we will take up we will take a ready-made example and finish off the things. Let us take a non-sway type of frame. So we will take this non-sway type of frame. Of course, it is quite a big problem only. Anyway, it doesn't take much time. A, B, C, D, E, F. So I will take UDL 60 kilonewton per meter, 4 meters. I will take a concentrated load center 80 kilonewtons, 4 meters, 4 meters. Or should we take 2 meters, 2 meters? Okay, that is better. 2 meters, that is this is also 4 meters. Then I will take an eccentric load 90 kilonewtons, 2 meters. So this 4 meters, 4 meters. Here I will take constant, that is simplified. So this you can analyze by say Kanis moment distribution. So as usual, the first step you have to identify what all the things you have to determine during analysis. That is the member and forces you have to determine. This is MAB, MBA, all in clockwise direction, local coordinate, clockwise direction, MBC, MCD, and MCD, MDC. These are the, of course, this MDC is 0, and here this is clockwise, clockwise, MBE, MEB, then this clockwise, clockwise, MCF, MFC. These are the forces at the ends of members to be determined. Then we have to find out the displacements also at the ends of each members, possible displacement. So here fixed ends, no displacement possible. Here only rotation possible, that is theta d. Here also rotation possible. Here also rotation possible. Then translation, vertical translation is ruled out because vertical members always fixed at the base. Horizontal member also. Here there is only one horizontal member in the total structure. It has one end fixed, another hinge. So horizontally also it cannot move. So that means no translation at all, either in the horizontal direction or in the vertical direction. So it is only non-sway type of frame. So that is your first step, non-sway, and these are the member and moment which you have to calculate. Then rotation factor you have to determine only at B, C and D. D is already known minus half because this A, D, F they are fixed. Rotation factor is 0, C is hinged, so it is minus half. Only at B and C you have to determine rotation factor. So at B, C, at B it is there are 3 members, BA, BE and BC. 3 members. At BA it is I by 4 and BE it is again I by 4 and BC it is I by 4. So total it is 3 I by 4 in the sum of the stiffness, relative stiffness value. Then rotation factor is I by 4 by 3I by 4, that is 1 by 3 into minus half, it is minus 1 by 6. Here also it is minus 1 by 6, minus 1 by 6. Mind it, the sum of the rotation factor should be minus half. whereas some of the distribution factor was 1 there. So that also you have to check in the beginning itself, the moment you have evaluated the rotation factor. At C also you have 3 members, CB, CF and CD. CB stiffness I by 4, CF I by 4, CD it is 3/4 of I by 3, that is also I by 4. So sum is 3I by 4 and rotation factor is, this is sum I by 4 by 3I by 4 into minus of, it is minus 1 by 6, minus 1 by 6, minus 1 by 6. Luckily we got all simple calculation. So now you prepare the Cornice moment distribution diagram. So as usual, now here there are totally 3 joints which are liable to be rotated. So those joints which are liable to be rotated, that you identify in this fashion. That is joint B, next joint C, next joint D. So these are the only 3 joints which are not fixed, wherein this rotation is possible. Then joint A, it is joint E, that's also fixed, it is joint F, that's also fixed. You prepare the diagram like this for doing Kanis moment distribution. Then you write this rotation factor, all minus 1 by 6 for BA, for BE minus 1 by 6, BC minus 1 by 6, CB minus 1 by 6, CF minus 1 by 6, CD minus 1 by 6, here it is minus half. That you have to transfer. Then you write fixed end moments. That fixed end moments you have to calculate. Fixed end moments. So that is MAB, MBA bar, they are equal because UDL, WL squared by 12, it is minus 60 into 4 squared by 12, it is minus 80. And MBC bar, MCB bar, it is WL by 8, that is equal to minus 80 into 4 by 8, that is minus 40. And MCD just now we worked out, that is minus 20, MDC 40. So this should not be a problem. By this time you should be master of finding fixed end moment, because we have solved slope reflection moment distribution right here. So here you transfer all those things, minus 80 plus 80 minus 40 plus 40 and minus 20 plus 40. Then find the total moment, 80 minus 40, 40, 40 minus 20, 20, 40. You transfer the total fixed end. Start doing moment, Kanis moment distribution, find out the fixed end moment, whatever you have to evaluate. Start with always from the left corner joint A, it is fixed, cycle 1, A, nothing. Then joint B, sum of the fixed end moment 40 plus contribution from this end, this end, this end, all zeros, all the 3 ends, it will be 0, it is 40 only, and that 40 is coming at B, that will be shared by this, so 40 by 6, minus 1 by 6, minus 1 by 6.
6.6.
So that is 6.7.
6.7.
That is, here also you can write here. You can write anywhere in this. Then you go to joint C, it is 20 minus 6.7 only. Here it is 0. Here also at the further end it is 0. It is 20 minus 6.7, that is 13.3. That 13.3 divided by minus 6, that is
minus 2.2.
Then here also minus 2.2. Here also minus 2.2. Then last here joint D, it is 40 minus 2.2. 37.8 into minus half, that is 18.4 minus. So this is your cycle 1. Here of course 0, 0, that is rotation. Then cycle 2 I will indicate it. First you can simply do on your own until consecutive rotation moment factors are same, no difference, not much difference. You can stop and apply same formula for finding the end moments of each member. For cycle 2, A as usual, nil, B, it is 40, here it is 0, there it is minus 2.2. You are getting a value. Earlier in the first cycle, all are 0. Now we are getting this, it is 37.8 divided by minus 6, that is 6.3. Minus 6.3. Minus 6.3. You can cancel the previous one. Then joint C, it is 20 minus 6.3. That is 13.7 into minus 1 by 6. That is
minus 2.28.
3. Minus 2.3 minus 2.3. Cancel previous one. Then D, you have 40 minus 2.3. That is 37.7 into minus half, that is 18.9. This you can cancel. Like that you can carry out the Kanis moment distribution. You can stop whenever that two consecutive rotation moments are same or not very much. Then you can find out MAB is equal to fixed end moment minus 80 plus twice rotation contribution at A plus rotation contribution at B plus space is not coming. So whatever value you got rotation at B, you take it. Here it is 0 only. Here that minus 80, you will get that particular MAB. On same lines, MBA will be plus CIT plus twice rotation contribution. Rotation contribution at the further end it is 0 MBAB. BA over BC, it is minus 40 plus twice whatever rotation contribution at this end. Here also it is 0 contribution from further ends. This you can complete it.
Yes.
Of course, that the answer you can verify. This I will circulate to you. You can verify at the end after concluding. That's all. Thank you.
So we started cycle 3. Cycle 1, cycle 2 is over here. Now we move on to cycle 3. In cycle 3, the joint A is fixed. So we don't want to carry that particular thing. So A is 0 because of fixity. Now this joint B is continuous joint. Hence we have to evaluate. So at joint B, first what is the summation of FEM? That is 40, 40. And what is the rotation contribution for further ends? What are the further ends? For joint B, AB is further end, here EB, here CB. So from AB, this is 0 contribution. Therefore, that is plus 0, 40 plus 0. From EB, here also because of fixity, 0 contribution plus 0. But from CB we are having minus 2.3. From CB we are having minus 2.3. So minus 2.3. So what is the thing? 40 minus 2.3?
37.7.
37.7. That 37.7 they have to contribute with the rotation factors. So 37.7 multiplied by minus 1 by 6. So or 37.7 divided by 6. 37.7 divided by 6.
6.28.
So minus 6.28 means minus 6.3. Here also the same thing, 37.7 divided by 6 minus 1 by 6. And here also minus 6.3. Here also minus 6.3. Minus 6.3. Now at joint C. At joint C, what is the summation of F here? 40 minus 20, that is 20. 20. 20. And what are the further end contributions? Further end contributions for C, that is BC, FC and DC. So from BC we are having minus 6.3. So 20 minus 6.3, here 0 plus 0. From here DC we are having minus 18.9. Minus 18.9. So what is the total? 20 minus 6.3 minus 18.9.
Minus 5.2.
Minus 5.2. That minus 5.2 divided by 6. That is minus 1 by 6. How much?
0.86.
0.86. That is minus 5 by 2 divided by 6. That is minus
8.6.
8.6.
Minus 0.8.6.
0.86.
86.
So
0.86.
okay, 0.9. Here also 0.9. Here also 0.9. Why this is 0.9? Because minus into minus, it will become plus. And also now I come to joint D. Joint D. For joint D, the summation should be 40. 40. From further end, the contribution is this one. 0.9 plus 0.9. It will become 40.9. 40.9 divided by 2. Divided by 2.
20.45.
So minus 20.45. So once we arrive the third cycle of contributions, we have to ignore the previous cycle contribution. We have to ignore the previous cycle contribution. So please ignore all the contribution from previous cycle and observe the difference of, we have to compare the values of both cycles. Here 6.3, 6.3 same. But if you come to this joint C, this is 2.3, 0.9. The margin is little high. So we have to carry one more cycle. We have to carry one more cycle. So that is cycle 4. Cycle 4. At joint A, 0. Joint A 0 because of fixity. Come to joint B. At joint B, what is the net FEM? Net FEM is 40. 40. What is the contribution from further ends? The contribution from further end is 0. Here 40 plus 0. From this end is also 0. Plus 0. But from CB, we are having contribution of 0.9. So that is plus 0.9. Plus 0.9. So we are getting 40.9. 40.9 divided by 6. How much? 40.9 divided by 6.
6.81.
So minus 6.8. Here also minus 6.8. Here also minus 6.8. Minus 6.8. Now I come to joint C. So when you come to joint C, the net FEM is 20. The further contributions are 20 minus 6.8 and minus 20.45. 20 minus 6.8 minus 20.45. How much?
Minus 7.25.
Minus 7.25 divided by 6. Divided by 6.
1.20.
1.20 plus 1.20 because minus into minus it will become plus. So 1.2, here also 1.2, here also 1.2. Joint D 40 and the rotation contribution from further end is 1.2. 40 plus 1.2. How much? 40 plus 1.2. That is 41.2 divided by 2. 41.2 divided by 2.
20.6.
So minus 20.6. Once we computed all the contributions, ignore the previous cycle contribution. Ignore the previous cycle contribution. So now once again observe 6.3, 6.8. Okay, marginally accepted. Here also 0.9, 1.2 marginally accepted. If you want, carry one more cycle or stop over here. I am stop over here because this is more or less near the values I am getting. So these are the final rotation contributions. Using these rotation contributions, we have to compute final end moments, final moments. So the next step is final moments. Final moments. Final moments. Final moments. First MAB. MAB equals FEM at AB plus 2 times of rotation contribution of AB plus 1 time of rotation contribution of BA plus sway contribution. Here it is a non-sway frame, so we are ignoring sway contribution. We are considering only rotation contribution. So now MAB equals, what is FEM? That is minus 80 plus 2 times of rotation contribution of AB is 0. Plus 1 time of rotation contribution is minus 6.8. So minus 80 minus 6.8, it will become minus 86.8 kilonewton meter. Minus 86.8 kilonewton meter. Similarly, MBA equals, the FEM BA is 80 plus 2 time of rotation contribution of BA minus 6.8 plus 0 equals, so 80 minus 6.8 into 2. 80 minus 6.8 into 2.
So 93.6. 80 plus 80 plus 13.6 is 93.6.
Wait, 80 minus 13.6. How much?
80 minus.
Minus 13.6. It will become
66.4.
66.4 kilonewton meter. MAB is over, MBA is over. Next MBC. MBC equals, FEM is 40, so minus 40 plus 2 times of minus 6.8 plus 1.2. 1 time of this 1.2. How much? So you are getting minus 40 minus 13.6 minus 53.6 plus 12.
Plus
Minus
12,
53
1.2 or 12?
1.2, not 12. This is only 1.2.
Minus 52.4.
Minus
52.4.
52.4. Minus 52.4 kilonewton meter. MBC over MBE. FEM is 0 plus 2 times the contribution at minus 6.8 plus 0. How much? That is 6.8 into 2. 6.8 into 2. 13.6.
6.
So minus
13.6.
13.6. See, just observe over here. To satisfy the joint equilibrium condition at member joint B, MBA plus MBC plus MBE equals 0. You just check over here. 66.4 minus 52.4 minus 13.6. Approximately the value is 0. Okay. So next MBC is over. MCB. What is MCB? plus 40 plus 2 times of 1.2 and 1 time of 6.8. How much? 40 plus bracket open 2 into 1.2 bracket close minus 6.8. Minus 6.8. How much?
35.6.
35.6. 35.6 kilonewton meter. MCB is over. Similarly, MCF 0, FEM is 0 plus 2 times of 1.2 plus 0. What is 2 times of 1.2?
2.4.
2.4 kilonewton meter. So you can check by joint equilibrium condition at joint C. MCB, what is the value of MCB? 35.6. MCF is 2.4 and MCD is, we have to compute now. What is the value of MCD? MCD equals minus 20 plus 2 times of 1.2, further 1 time of 20.6. How much? That is minus 20 minus 20.6. It will become minus 40.6. Minus 40.6 plus
2.4 is 38.2.
Minus 38.2. Yes. Now to satisfy, you can check the joint equilibrium condition whether it is satisfying or not. That is the member. What is the final end moment at joint? MCB plus MCF plus MCD equals 0. That is MCB. MCB is 35 plus 2.4 minus 38.2 equals 0. Yes, more or less it's satisfying because if you add this, you are getting 38 and plus 38 minus 38, it will become 0. Finally, MDC. MDC equals 40 plus 2 times of minus 20.6 plus 1.2 is more or less we are getting 0 because the last end is hinge. So and one more thing we are remaining with MFC. MFC we have to compute. MFC equals the FEM is 0 plus 2 times of 0 plus 1 time of 1.2. We are getting 1.2 kilonewton meter. Totally we have to arrive at one member 2 moments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Totally 10 moments we are arriving. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So MEAB, MBA, MBC, MCB, MBE, MEB. MEB we have to arrive. MEB, then FEM is 0. FEM is 0 plus 2 times of 0 plus 1 time of further end moment is 6.8. That is minus 6.8. We are getting minus 6.8 kilonewton meter. So finally we are at 4 plus 6, 10. The last step is plotting the bending moment diagram. It's very easy to plot bending moment diagram for this type of structures. So the thing is, here we are having UDL. The free BMD is in the pattern of parabola and the value is WL square by 8. Here you are having a central concentrated load. Therefore, this is WL by 4. Here you are having eccentric load. It's also triangle. WAB by L. WAB by L. This is the free BMD. Just substitute the values. You are getting free bending moment diagram. Now, how to impose these final moments? How to impose? MAB. Just check here. This is A, B, C, D, E, F. So MAB is minus 86. See, minus means anti-clockwise. Minus 86.8. So it's a tension zone. Arrow head is compression zone and the bus is tension zone. Always plot the whatever the bending moment diagram in tension zone. So mark 86.8. So this is 86.8 kilonewton meter. Similarly, BA. What is BA? Clockwise. Clockwise, the value is 66.4. So this is 66 clockwise. So once again, this is tension zone. Here you are plotting 66.4. And find this value and impose this. And impose this to 66. Join this. Okay. Next, BC. The BC is minus 52. So minus 52 anti-clockwise. 52 or 53. Just mark here. Okay. Next, CB. BC or CB. CB is 35 clockwise. So approximately I am taking 36 clockwise. So you just mark here 36 and join this. This is 36 and this is 53. 53. 53. Next, CD. CD is 38. Minus 38. Minus means it's anti-clockwise. 38. So this is 36. So 38. 38. And DC is 0. Just join this. Is 0. And here you just observe here BE. The BE is anti-clockwise. B is here. And EB. EB is, that is also anti-clockwise. That is 6.8. 6.8 anti-clockwise. 6.8. And BE is anti-clockwise. 13.6. 14. So just join here. This is 6.8 and this is 14. Similarly, CF. CF is clockwise 2.4 and FC is also clockwise 1.2. Here to here. This is 1.2, 2.4. So this is regarding bending moment diagram. So we are just imposing free bending moment diagram as well as final moments in one FEM, one final bending moment diagram. This is the case regarding non-sway Kanis method, non-sway frame using Kanis method. So the very simple steps what we have followed in this particular methods are: first we identified the kinematic indeterminacy. Here we got by that particular thing we got to know that the given frame is non-sway frame because we got only rotations as unknowns. Next, what we had did, we computed the rotation factor. How to compute rotation factor? This is nothing but similar to distribution factor what we discussed it in module number 2. The rotation factor is nothing but minus half the times of distribution factor. In distribution factor we are getting 1 is the thing. Here we are getting minus 0.5. So at fixed joint we are not getting distribution factor. If the end support is hinge, roller or simple support, the rotation factor is minus half or minus 0.5. So in the given problem, joint A, E, F are fixed. We are not getting any rotation factor. But joint B and C are continuous joints, that is continuous supports. So we have to compute rotation factor. What is the rotation contribution of each member and members meeting at a joint B and joint C. And finally at joint D we are having hinge. We are getting rotation factor of minus half. Once we computed the rotation factor, the next step we move on to FEM. So general procedure we adopted whatever we following in SD method and MD method. The similar way we are assuming each members to be fixed and we computed the fixed end moments. For example, at member AB we computed using a standard equation MEAB bar or MBA bar equals minus WL square by 12. Similarly, if a load of point load carrying at a center, then that is minus WL by 8. If it is eccentric load, then minus WAB square by L square and minus plus WBA square by L square. Using those standard whatever formula we have given already, using those things we have computed FEM. Next, we obtained the Kanis moment distribution table. It's a pictorial representation. So at fixed end we are not getting any distribution things or pictorial representation, only at continuous, and if the end support is fixed, simple roller, then only we have to represent in pictorial way, and we just carried the more or less 1 to 3 cycles, generally 3 to 4 cycles we are getting the matching values. So we have to carry the cycles in a such a way that the two values should be nearer or equal or same. So how to carry those cycles? The first thing is we have to write the rotation contribution factors. Rotation factors, what we computed in previous steps, we have to write in these smaller boxes, and we have to write FEM here. FEMs, these are FEMs computed, and at the middle of this is net FEM. At joint B, the net FEM is 80 minus 40, 40, and 40 minus 20 is 20, and 40. So at center box we have to write net FEM. Next we have to compute subsequent cycles for rotation contribution. How to compute rotation contribution? I have written the equation. The MAB rotation contribution, MAB equals, is not MAB, it's a rotation contribution. Rotation contribution, RMAB you can take, RMAB. This is final moment, but rotation contribution we have to write like cycle 1, cycle 2, cycle 3. Rotation contribution is nothing but, if you take rotation contribution RAB, rotation contribution RAB, that is nothing but net FEM at joint B. Say for an example, joint B, the member BA, I am accounting BA, joint B, BA, that is net FEM. Net FEM is nothing but whatever at the box we are highlighted, 80 minus 40 is 40. Net FEM plus rotation contribution from further ends. If you are accounting BA, for BA you have to see the, for joint B we have to see the what are the further ends. For B the further ends are A, E and C. From A, E and C, what are the contributions? That we have to add. A here 0, here also 0, but here we are getting the contribution of 1.2. So this is the thing, and finally we have to multiply that particular thing with rotation factors. We are getting these next cycle subsequent values. Finally, what we obtained, the final values. Using these final values, we have to compute final moments. For final moments, the equation you have to remember is just like a slope deflection equation. That is FEM plus 2 times of rotation contribution from particular end. If you are looking AB, that is 2 times of RAB. If you are looking BA, then that is 2 times of RBA and 1 times of RAB. Similarly, in one member we are having 2 ends. What you are exactly looking, you have to see that. You are looking AB, then 2 times of rotation contribution of AB and 1 time of rotation contribution of BA. Similarly, you are looking the member BA, then 2 times of rotation contribution of BA and 1 time of rotation contribution of AB plus that particular FE. That is the final end moments. Finally, using the concept of whatever the tension zone, you are representing whatever the moment, bending moment diagrams, and we are imposing the whatever the particular simple bending moment diagrams. That is by using the standard equation. If the simple bending moment diagram is like, if your span is carrying UDL, WL square by 8, its central concentrated load WL by 4, and if the eccentric load WAB by L. Using that equation, you have to compute the and arrive the bending moment diagrams. These are the general steps what we followed to solve a non-sway frame using Kanis method. Thank you for watching.